So just a little triangle review. We've learned so much. I don't think this is on your paper here, so we're just going to answer by looking up here. The sum of the interior angles of a triangle is 180, right? The measure of an blank angle is the sum of two non-adjacent interior angles. You remember that, Lee? Exterior angle, right? That's that one where this one equals that plus that. Yeah, that one. The non-right angles of a right triangle are, I'm not sure you know what I want you to say here. The non-right angles, so you have a right triangle. What do I know about these two angles? Huh? No, they could be, but not necessarily. But there is something else I know about them. What do you think? They add up to 90. What's another way of saying they add up to 90? Huh? Complementary? I think that's what I got here. Complementary. The base angles of an isosceles triangle are. What do I know about the base angles of an isosceles triangle? Congruent. We just did that one. A triangle is equilateral if and only if it is. What do you think goes there? Yeah? Equiangular? And a right goes backwards, so if it's equiangular, it's equilateral. And two triangles that meet the requirements for SSS, SAS, ASA, AS, or HL are congruent. Which are the ones that don't work? Which ones don't work, Amanda?
SSA and AAA.
Yeah, these are the ones, well, we'll put the internationalization somewhere there. Those ones don't work. Okay, so let's look at some vocabulary now. Oh, there's a lot in this one. This one, it's not that it's so difficult or hard. There's just a lot of new words, A mid-segment, okay? So now we're on your notes. Mid-segment. It's a segment that connects the somethings of two sides of a triangle. Do you know? The midpoints. Yeah, so that's what goes in that blank there. And it says, like, make a picture. So it connects midpoints. So here's a midpoint, and I know it's a midpoint when it's got two congruent pieces, right? And maybe that's another midpoint. So if you connect them, that's called a mid-segment. Okay? So I think the picture helps. It does for me, because I'm real visual. I'm kind of helps me to see it. Okay, so in that blank, make a little picture of that, mid-segment. So basically, yeah, the midpoints are connected. Perpendicular bisector, I think we know that. We've constructed these anyways. It's a segment, ray, line, or plane that is blank to a segment that is blank. Like, the blank is a blank. Like what? What do you think? Yeah, I like midpoint, and it's a perpendicular bisector, so it's perpendicular. Yeah. So what does that mean? So if you have a segment, a perpendicular bisector bisects it, and it's also perpendicular to it. We built these when we did our construction. Perpendicular bisector does two things. Angle bisector, this was one that was a little confusing for some people. 2 checkpoints ago I noticed that. An angle bisector is a segment, ray, line, or plane that divides an angle into two angles that are... I'm hanging here. Amanda, what are they? Congruent. They are congruent. Okay, so the picture there would be if you have an angle, then the bisector makes two congruent angles over here. Angle bisector. Alright. This one we should be somewhat familiar with. Now a median. A median is something else. It's a segment from a vertex to the blank of the opposite side multitude. Do you know what that is? Midpoint. It is a midpoint, yes. So let's say if I want the median in a triangle, so this would be like, say, a midpoint here. So it's from the vertex opposite it. This would be a median. It connects it to the midpoint, a vertex to a midpoint. Vertex to a midpoint. Question?
Yeah, I mean, you can't do that with a square, right? It's a vertex and just the opposite.
Yeah, I think we're mostly thinking about triangles. But I guess we can have it in other polygons too. We can have it in other polygons. For us right now, we're just worrying about triangles. Yeah.
Are we supposed to memorize them?
Well, ish. I mean, yes, 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 yes. An altitude, yes. You do have to know what an altitude is. An altitude is a blank segment from a vertex to the opposite side. You have to sometimes extend this side. It's dropping a perpendicular. An altitude is a perpendicular. I'm running out of space here. So let's say it's in a triangle. So let's say from here I want to drop an altitude. It's dropping from the vertex a perpendicular. And we'll talk about why sometimes it has to be extended. We'll talk about that a little bit more. So it's basically the height of this figure. That's the height. What does it take?
A segment from a vertex that is blank. The opposite side.
Okay. All right. You know what it means? You know what I want you to say there? Okay. Equidistant. A point is equidistant from two figures if the point is the blank distance from each figure. Okay. So how do you draw equidistant? There's any number of ways. So I'm just drawing two figures here. So if you have a point and it's equidistant, so you drop, you actually drop perpendicular to it, but it's the same distance. This point is the same distance, and distance we usually measure in perpendicular, but equidistant, same distance. Now a point of concurrency, like the word to have things concurrently in real life, does that mean that things are concurrent? What does that mean to be concurrent? What does that mean? What does it mean? Go ahead. Yeah, like same, right? Concurrent? Often kind of at the same. So a point of concurrency is a point where lines in a triangle, such as medians, altitudes, and bisectors, intersect. It's where they all meet up. So I don't know how do you make a picture of that. So this one, this one. If they all meet up in the same place, that's a point of concurrency. Yes, sir. What? Well, maybe. There's all different kinds, so that's what we're going to be talking about. So do I have to know what a midsegment is? You kind of do. It's a segment that connects the midpoints. Do I have to know what a perpendicular bisector is? Yes. Angle bisector? Yes. Median? Yes. Altitude? Yes. Do you have to know what equidistant means? Yes. I'm going to say kind of. Yeah, you do. Yes. Okay, so we're going to kind of focus on each of these different things. And again, this may get a little confusing. It may get a little frustrating. The first time you hear it's going to be like, this one does this and that one does that, and maybe like a jumble. It does sort itself out. So just bear with me. Okay, so again, what is a midsegment? A midsegment is a segment that connects the midpoints of two sides of a triangle. So here we go. Here's my triangle. I know it's a midpoint because I can see these little congruence markers. What were we talking about? Yeah, so we've got this thing here. So there's certain little properties that apply to this. Here's a theorem. The segment connecting the midpoints of two sides of a triangle is parallel. First of all, here's one thing. It's parallel to the other side, and it's half as long, which means, like, say if this one was 4, then this length would be 8. That's what I mean by it's half as long. The midsegment is half the size of that opposite side, or I guess you should say parallel side. Okay, so the midsegment is parallel to the side of the triangle that it does not intersect. So it's the one that kind of makes sense. That's what it's parallel to. It's half the length, or you could say this one's twice the length of that one. Every triangle has exactly 3 midsegments, doesn't it? So what do I mean by that? So if I'm connecting midpoints, so from this midpoint to that midpoint, and that midpoint to that midpoint. So I've got 3 midsegments. This one will be parallel to that side, and this one will be parallel to that side. This one, half the length of that one. This one, half the length of that one. This one, half the length of that one. Let's see what we can figure out here. Now, if this is 4 and this one's 8, what does that make this segment and this segment length? Very short, right? So look at that. This one all congruent. So let's say this piece was 6. What else is going to have a length of 6? Right, if VE is 6, what else is 6? Amanda, what else is 6? BC. I've got one other segment that I know is 6. There it is. This piece that's parallel to it is half the size of this piece. So this whole piece is 12, right? So what's this piece? 6. So notice how they kind of all match up. If this piece was, I'm just making up numbers here, I don't even know if they make real triangles, if this was 7, what else is going to be 7 long? This one? Yeah, these two guys. Whole thing is 14, which is half of that, and because it's a midsegment, it divides them in half. The 3 midsegments create 4 congruent triangles. All these triangles are congruent. Look at the sides. 4, 6, 7, 4, 6, 7, 4, 6, 7. You get side, side, side congruence with them. So kind of interesting things happen. Yeah. Triangle in between the midsegments. Meaning
There. So, that one.
here.
Yeah.
So you're making another set of midsegments? Oh, you can do this forever. I know.
Midsegment
Take a look there.
section.
Tell me what
Yeah,
you
they
mean.
call it the fractal.
It is kind of a fractal, isn't it?
You can do that with all of the triangles.
I got my pen out of the way, sorry. My pen's out of the way, it's because mine was in the way, sorry.
Triangle, like right here.
Yeah?
Isn't that a triangle? So what that would be congruent triangle?
Well, it's congruent to this one, this one, this one, and this one. Those are my 4 congruent triangles.
It's out of the
Yeah, I'm sorry about that. That's what I mean by 4 congruent triangles. The small little ones we created are all going to be congruent by side, side, side. How fun is that? So looking at some examples of midsegments, let's see, ST and TU are midsegments. So here we go. Here's ST, here's TU. Find the length of PR and TU. Well, let's start with PR. ST is an 8. Okay, that's an 8. So what's the measure of PR, Joseph? 16, right? It's twice as long as that one. If I'm turning this way, this whole thing, PQ, is 10, and TU is a midsegment, so what's the distance, what's the length of this guy? This one's 10, so this one is? Come on, I think I need more than one person kind of getting it, Kaya, what do you think? 5. Just take half. So midsegments are parallel, and one is half the length of the other. Okay, what's going on with B? XZ and ZY are midsegments. And usually when I hear that, what I like to do is, okay, I just automatically, I don't know if I need it or not, but because they're midsegments, I know what that means. Let me say XY is, okay, yes, I guess this one also. Find MN and ZY, right, MN. That's this big one. It looks like, what is that one? Okay, this one is 26.5. So what is this one going to be? What's that going to be? 53, right? 26.5 times 2. Twice as big. And then they also want to know what VY is. That's this one. So I'm looking over here. Yeah, this one's 28. So this one would be 14. It makes sense. You're just taking half. ED segment here, they're midsegments. ED is a midsegment, so these are midpoints. And also DF, that's a midsegment, so we've got 3 points here. Find DF, this one, and find BC. All right, DF is going to be 7, because we're looking at that opposite side there, or the parallel side. And then BC, I want this guy. What's that one going to be? See, that's an 8. Oh, no, read this one. No, look at that one. 6. Right, this one's a 6. So what's this side? Yeah? 12. Let me ask a question if you're like, where are the numbers coming from? If you have that question, please ask. Alrighty, what else do I know over here? SB is congruent to SC, which makes it a midpoint. RS is parallel to AC. RS equals half of AC. So if this one is X, then this length is 2X, half of it. Show that R is the midpoint of BA. Whoa, how do you do that? How do we know R is the midpoint of BA? Joseph, what do you think? I cannot hear you, that's real loud.
Since RS is a one half AC, RS is a midsegment.
And it's parallel.
Midsegment of AC.
Right.
So R and S are equal.
Yeah, so yes, because, remember that was an if and only if here. Since this is half the length and parallel, then this is a midsegment. If it's a midsegment, then like this has to be a midpoint. And that's kind of it just has to be, because that's the rule with midsegments. Okay, midsegment, done. One down. We have 2 more to go. We're going to look at perpendicular bisectors. At least this one I think we're a little bit familiar with. Definition. Oh, look at that picture. A segment that is perpendicular to the side of a triangle at its midpoint. So it's a segment here, and it's a perpendicular bisector. If you were to extend this, does it necessarily go through the vertex? Not necessarily. So they don't necessarily go through the vertex. Perpendicular bisector theorem and converse, so it's an if and only if. In a plane, a point is on the perpendicular bisector of a segment if and only if it is equidistant from the endpoint. Okay. So here's a segment, here's its perpendicular bisector. Since it's a bisector, I know those are congruent. If you pick any point on this bisector and you draw a line to the endpoint, you have the same value. So any point on here, these pieces are congruent. Well, not necessarily with this one, but they're the same distance. Okay, that's what it's saying. Oh goodness. Perpendicular bisector intersects at a midpoint. It's going to be a right angle. Any point on the perpendicular bisector is equidistant. That's what this picture is. Every triangle has exactly 3 because it has 3 sides. The point of concurrency, so here we're getting to all these fancy words now. It's called a circumcenter. If you were to draw all the different perpendicular bisectors, it will meet at this particular center, and it's called a circumcenter. And it is equidistant from the vertices. So this point where all these things meet, if you were to connect this point to all the different vertices of the triangle, they are congruent values. Oh. So this is a true word. I am not going to be testing you on whether you know this word, but if I use it, you may have to say, well, what does that mean again? We have to know what that is. Yeah.
The triangle, it doesn't always fit perpendicular.
Doesn't have to. Remember, it's just somebody's drawing. You have to go by what it says. If it says it's perpendicular, it is. Okay, so go by the little marks, not by what it looks like. All right, so looking at some examples for these, let's see. KM, I'm looking here. Here's KM, and it's perpendicular bisector of JL. So perpendicular bisector, I would draw in what that means. It means that you have a bisector, so these segments are congruent, and that this is a right angle, and it's on both sides. They want us to find JK and JN. Let's do a look right here. JK and JN. Oh yeah, okay, that's fine. They want us to find JM and JK. So let's see. You can remember the theorem that says equidistant, right? So it must be that this piece is congruent to this piece. Now, if you're given this problem and it shows up and you don't remember it, there's kind of another way to kind of remember the theorem. These 2 sides, because it's a bisector, right? We know that's congruent. Since this is a right angle, so is this one, right? And this is the same thing. So this triangle on the left is congruent to the triangle on the right. So these are congruent by CPC2C. It's just another way to kind of get there, because I'm throwing a lot of stuff at you today that might not stay in. So if you're thinking, well, they probably want these to be congruent. Why would they be congruent? Oh, okay, I can see some congruent triangles. I know they are. So it's just a way to remember that. So these two things are going to be congruent. I also know, because it's a bisector, that those things are congruent. So these are the two equations we want to solve. Okay, yes, sir? Question? Well, yeah, we're just going to have to do it, right? Subtract the 3x. So I'm getting x is 4. Let's see, I'll put that one over here. So 9 equals 3y. Looks like y equals 3. If x is 4 and y is 3, and they want us to find jm. Oh, jm is this one, 7 times 4. It looks like jm is 28. They also want us to find jk, which is this one. Jk is going to be 2 times y, which is 3. 6 plus 9, 15. Yeah. Okay. All right, so BC. BC is a perpendicular bisector. It's a line here of AB. So it's the perpendicular bisector of that. That means this, congruent to that, and they did put in the right angle marker. I put them in, I don't know if I need it or not, but it's there. And AE, where's that? AE, okay, what's this one? It's going to be congruent to BE. What's this one? Sorry. Okay, so I'm putting in what they're telling us. What segment length must be equal? Well, the one they gave us for sure has to be equal, right? BE has to equal, length of BE has to equal length of AE. And because it's a bisector here, that means that BC's length has to equal AC's length. And do I have any other lengths that are congruent? Amanda, what other lengths are going to be
AC and
congruent?
BC.
Which one?
AC and BC.
I've got AC and BC. I'm looking for another one. I've got BE and AE, AC and BC. I need one more. One more. You see what Joseph? Talk real loud. Which one?
Maybe.
This one and this one, because of that theorem that says that all points on a perpendicular bisector are equidistant from there. So this is congruent to this one. Then I have a question. Is point E, if you were to extend CD, would point E be on it? Really, why is that? Just so you know that.
Because the segment lengths are equal,
Yes.
and so the line, the point at which this two segments meet, so this length are more than one equal.
Yes. Because these two segments are congruent, so that means the point where they meet is equidistant from there, which means it must be on the perpendicular bisector. Excellent. Very nice. Oh, perpendicular bisectors. Now we're on angle bisectors. Woohoo! Now we should know what an angle bisector is. It's a segment, ray, line, or plane that divides an angle into two congruent angles. Now if you're looking at it within a triangle, oh, what's happening? So we have a theorem. A point is on the bisector of an angle if and only if, so bidirectional, it is in the interior of the angle and is equidistant from the two sides. So whenever you have an angle bisector, and you kind of extend these guys, when you measure a distance, you always drop perpendiculars. That's how you measure distance. So this one will be congruent to that one. Anywhere on here that you drop perpendiculars to get distance, you're going to have congruence. Angle bisectors. Oh. An angle bisector creates two congruent angles. You know that. The distance from a point on a line, point to a line, is the length of the perpendicular segment. So making a distance is dropping perpendiculars. Any points on this angle bisector will be equidistant from the two sideways here. Every triangle, now if you draw these angle bisectors, and now they are going through vertexes, it has exactly 3 because there's 3 angles that you can bisect. And now we've got a point of concurrency. In-center is what we call it. If it's angle bisectors meeting up, called an in-center. And it is equidistant from the sides of a triangle. So if you were to kind of drop a distance, how far, they're the same distance from an in-center. So these are more than nice to knows. This is the stuff you kind of need to know. It's not as complicated as it sounds. Let's look on top of page 3 here. Find LM. Find this length. So that the key here is noticing that this is 34 and this is 34. So that makes this a bisector, right? It's an angle bisector. because you see these two congruent angles. What do I know about points on the angle bisector? Yeah? They are equidistant from the sides of the angle. So this one is 5, and that one has to be 5. So these are congruent pieces. Alright. Looking at example B, for what value of x does P lie on a bisector? So when is it on a bisector? When these are congruent and they're the same thing. So these have to be a bisector. So that means that this angle has to be congruent to that angle. So we're going to set them equal to see what x has to be. Subtract that. 2x equals 8. It looks like x has to be 4. Because if x is 4, you will get congruent angles here. So that means I'm on the bisector. Okay. You with me? Alright? It's not like they're hard, there's just a lot of them. V is the in-center, meaning that it's where all the angle bisectors meet up. So these are all bisectors. So in my drawings, I would do this just because it will help me remember. Okay, I've got bisectors. That's what an in-center does. And they want you to find the length of VS. Oh, that's this one. Okay. I do know that VS and VT are congruent. Why do I know that? VS and VT congruent? Because what? I can't hear you. Yep. Yes, because the distances, it's on a bisector, so the distances, I know it's a distance because I see the little right angle markers, they have to be congruent. And I'm honing in on this triangle here. Pull that out a little bit. Can I find this side? Because if I find this side, I found that side. Right triangle. Right? You can use the Pythagorean theorem. So x squared plus 15 squared equals 17 squared. X squared plus, is it 25? I think that's 39. Okay, subtract that guy. X squared is going to be 64, I think. So x is plus or minus 8. Well, I'm going to reject the negative 8 because it can't be a segment. So that makes x 8. That's this way. But because it is on that angle bisector line, the distances have to be the same on either ray. So VS will also be 8. Wow. How many more of these are there? Just 2 more. Just 2 more. Okay. Again, I'm going pretty fast. There are other questions. It's not that any of them are so difficult, it's just it's a bunch. Alright, let's look at median. Now, so if you recall, the median is a segment from a vertex to the midpoint on the opposite side. So what's the difference between a median and a mid-segment? What's the difference between these two things? Besides Joseph, he's the only one who knows anything, my goodness. What's the difference between a mid-segment and a median? Julie, do you want to take a stab at it? Well, they both connect to midpoints, right? So they do both connect to midpoints, and that's what they have in common. What do you think, Amy? Median is from midpoint to vertex. And what about mid-segments? Midpoint to midpoint. So a mid-segment does not touch the vertices. A median does. Distance from vertex to midpoint. So it's a different thing. So what do we know about them? The endpoints of a median are a vertex and a midpoint on the opposite side. You have a vertex and a midpoint. It creates two congruent segments on the side that intersect. What? This one and this one. So because it's a midpoint, you've got these two congruent pieces. You've got 3 medians because you have 3 angles. The points of concurrency. Joseph, this is a centroid. We were talking about centroids before. If all the medians in a triangle are drawn, they will meet at a centroid. And this is kind of a cool thing. The distance from a vertex to the centroid, from here to here, is 2/3 of the whole thing. Which means the distance from a centroid to the midpoint is 1/3 of the whole thing. So what? So if I've got a whole bunch of medians here, and let's say this whole thing is 12, what would the length of this piece from the vertex be? 2/3 of 12, which is would be 8, and then 1/3 of 12 is 4. So they kind of break up that way. Wow. Okay, so let's look at a couple median examples here. So a triangle ABCD is a centroid. Okay. Well, that means that I have medians. So like this one goes here and that one's here. Just to remind myself that I've got medians. Let's see. BD. Oh, it's the same example I just did. It's 12, right? So what is DG and BG? So now you got to figure this out. There's many ways to kind of think about it. One way is to say, I know 12 is equals 2/3 of the whole thing. So it's kind of saying it out loud. 12 is 2/3 of the whole thing. So I can solve this by multiplying both sides by that reciprocal, right? 6. So I'm getting 18 is BG. So the whole thing is 18. And this small piece is 1/3 of the whole thing. Whole thing is 18, so this would be 6. Yes? You can also think of this as, in thirds. So this piece is 2 of them. So there's 2 of the 6's here, and there's 1 of the 6's there. If you see it that way, that's fine too. Some people have trouble seeing it that way. Okay, so that's kind of the trick with that. Let's look at PQR. S is a centroid, meaning you've got medians. UQ, now it's this one, right? Look at it. Oh, it's tiny. UQ is, oh, there it is. 5. That's this guy. Yeah, TR is 3, and SU is 2. So we want to find RU, which is this one, and we also want to find RS. Now I don't want an answer. I want how. Don't just you shout out, I know it. Okay, they're giving me this one's card also, right? So you have to tell me how. If you shout out an answer, I'm not calling on you. So how? How do you find, say, RU or RS? You think? Evan, how do you do this?
Since you know that 2 is 1/3 of the whole thing,
Okay.
you know that RS is not only 2/3 of it,
Right.
you just have to double 2.
Right, so if this was in thirds, this would be 2, this would be 2, and this would be 2. So the whole thing is 4. You can also think about 2 is 1/3 of the whole thing, right? 2 is 1/3 of the whole thing. Multiply both sides by 3. The whole thing is 6. Since that one's 2, that piece is 4. So either way, they're both fine. So RU is 6 and RS is 4. Now it wants to find the perimeter. Oh, how am I going to find the perimeter, Keely?
Since you have all the numbers 5, 5, and 3, so all you do, since they are all half of 6
They're all midpoints. You're using the right word. I know we had too many words. Midsegment median.
and so you just put 3 on the other side, 3, 5, and 5.
Right. Because these are medians, it's connecting at midpoints. So you know one piece, you know the other piece. So this side is 10, right? This side is 10. This side is 6, so it looks like the perimeter is 26. Good. Excellent. Very nice. Medians. Okay, last one. Last one. Promise. Okay. Altitudes. Altitudes are kind of an important thing, and they will remain important. So it's a segment from a vertex. So you're starting from the vertex, and you're dropping a perpendicular to the opposite side. You do not necessarily get equivalents. They are not necessarily midpoints, only in special circumstances. So you're just dropping that, and it's how you measure heights in a triangle. Dropping a perpendicular. You can drop one from each of these vertices. The endpoints of an altitude are a vertex and a point on the opposite side that is perpendicular. The altitude and height mean the same thing. So when you're doing like area of a triangle and it says 1/2 base times height, height is an altitude. Has to be perpendicular. Yeah. Yeah, we're going to look at a right triangle. He's absolutely right because of that perpendicular. Yeah, hold on to that thought. You're right. The point of concurrency. So all the altitudes in a triangle will meet up at a point called an orthocenter. Okay. Now sometimes you will, the height is outside. So if you have an obtuse triangle, obtuse, right? And I want to know, gee, what's the height from this vertex? If you go straight down, you kind of have to extend that side. So it's outside the triangle. That happens. It could happen. But if you look at this one, from this side, the height is this way. So it can be different depending on where you're dropping your height. So this is kind of a good little example here. Find the orthocenter, meaning I'm going to look for where they all meet up, these altitudes. So this is an acute triangle. So I can drop one, it's about here. I'm doing an estimate. It's about here. And this one is going to be about here. So if you have an acute triangle, it looks like this. Now coming back to Evan here, if this is a right triangle, well, if I drop one from here, right, there's one of them. But from this vertex, if you drop one, it's the side. If you drop one, it's the side. So when you're finding area of a right triangle, and you said 1/2 base times height, it's going to be, the height is one of the sides, usually. Okay, so yeah, they meet up over here. Now it's a little bit more complicated when you have an obtuse one. So this one I can kind of see. That goes there. Now this one, oops, I'm trying to extend the side straight here. That's going to go there. And then this one. Oh, okay, so this one, I guess I have to do this side. And I think that's right. Eventually they do actually all meet up. To like extend and extend. So your orthocenter is that way outside of the triangle when you have an obtuse. Yeah. There's one orthocenter, it's right here. It's just well, it's because it's the actual height is the side of the triangle, so you can't see it as well, but it's there. It's still a an altitude. Yep, they all have 3.
The rest of them are from the other
Yes.
side.
Yes.
So,
Yes. Yeah, right triangles are a special case, and the obtuses you kind of really have to think about it too. Look at a summary here. Let's just look at some summary stuff, because there's so much. So I think would be a great thing to do. We have plenty of time. I want you to draw a sketch. So let's just do midsegment together, so you know what I want you to do here. So a sketch of a midsegment would be, maybe draw that you've got some midpoint there. If you want to draw all of them, you could. If you want to do that, you could. Does it always intersect at a vertex? No, this one doesn't touch a vertex, does it? Always intersects the midpoint of a side. Is that true? Sure does. Right? You're going to get midpoint. And it's always perpendicular to a side midsegment. No. This does not have a point of concurrency, so it doesn't work. Give it a try. See if we can fill out the other pieces to this, and we'll compare and see how it would be matched. While you're working on this, one thing you might want to do is write down maybe the important things about it. Like it's parallel, right? And it's half the length of the side. And just little things that might, so that you only have one thing to worry about. Medians, it's like 2/3 from the vertex to the centroid. Just looking at some of these important things. This one is points on right. start working on homework, it starts to gel and come together, and it's not quite as complicated as you might think. So I recommend if you haven't quite finished it, maybe copy some of this down, and then we will get ready to